Okay, let's continue then with number 5. So we've got a triangular area in a park surrounded by 3 sides of a triangle, and the measures, strange, the 50-degree angle didn't appear on the diagram, did it? So let's just make sure that we add it. So we've got a 50-degree, measure it right there. Now obviously if this is 50 degrees and this is 30 degrees, that makes a total of 80. Seems silly not to immediately find the third angle in the triangle. Find the length of AC. So we're looking for this length right here. Now this is clearly not a right triangle, so we cannot use SOHCAHTOA nor Pythagoras. So let's see if we have an opposite pair. It turns out that we do, and as a result we can use the sine law. And so let's set up that opposite pair, that the sine of 30 degrees divided by 400 is equal to the sine of 50 degrees divided by the value that we are trying to find, which is the length of AC. I'm going to call it x. You'll notice that I've set up the opposite pair for that one as well. Let's cross multiply then. So x times the sine of 30 degrees equals 400 times the sine of 50 degrees. And I'll divide both sides by sine of 30 in order to get the x alone. And so let's see what I get when I type in 400 times the sine of 50. Make sure I close the brackets. So it's that result divided by the sine of 30 degrees. Oops. So 30 degrees, close the brackets. Okay, I've got 612.8. If I round to 3 significant figures, then AC is approximately 613. My units are meters for its length. Diana goes along these 3 paths in the park at an average speed of 1.8 meters per second. This S-1, by the way, it's like saying 1 over S. So when you've got meters times seconds to the -1, you're really just saying meters over seconds. It's an IB notation for saying meters per second. They're identical, okay? So she goes along at a speed of 1.8 meters per second. Now, you can see what's happening, right? They're going to create a velocity equals distance over time problem, where we've currently got our distance and our velocity. I bet you they're going to ask for our time. Let's have a look. Given that BC is 788 meters, all right, thanks for the free information. That one's 788, and we already found that this one was approximately 613 meters. How many minutes does it take for her to walk once around the park? Okay, so the total distance that she's traveled is 400 meters plus 613 meters plus 788 meters. That gives us then 400 plus 613 plus 788. In fact, it wasn't exactly 613, was it? I'll tell you what I'm going to do. I'm going to come back. Instead of 613, just a minute, delete. I'm going to say, let's bring up the answer that I just had, which was the exact value, 612.83555545, plus 788. There's my total distance, 1,800 point yada yada yada. So it rounds to approximately 1,801 meters all the way around the park. So now if velocity is distance over time, if we rearrange this equation and bring the t upwards to the left-hand side and the v downwards onto the right-hand side, you'll find that t is equal to d over v. Now if you have difficulty with that kind of stuff, another way of doing this is to remember there's a little triangle where the d is on the top and we have tv on the bottom. And so this means then that distance equals time times velocity. Time equals distance over velocity, and velocity equals distance over time. So you can see the velocity is distance over time here. Here's the time is distance over velocity, the one that we need because we're being asked for the time. Our distance is 1,801 meters, and she's walking at 1.8 meters per second. So let's see what we get. 1,000. Well, I'll take my exact value, in fact, the answer that I just had, which is an even more precise amount for the distance, and we'll divide it by 1.8. And it takes 1,000.5, let's say, 1,000.5. And what is the unit of time that we're dealing with? Well, we had the meters over meters, they cancelled. The seconds is the only thing that's left. So this must be the amount of seconds. But we're supposed to find out how many minutes it will take her. So let's divide this amount then by 60 to find out how many minutes. And if I round to three significant figures, it will take 16.7 minutes. Alright, let's move on then to number 6. So that's a side view of a tent. The tent is 6 meters high. The ground slopes upwards from the bottom of the tent at an angle of 5 degrees. So if this amount right here is 5 degrees, well then the remaining amount must be 85 degrees, because of course the whole thing is a 90-degree angle, isn't it? So calculate the angle BAC. Oh, well, I've just done that, haven't I? It's 85 degrees. Okay, it's obviously 90, the right angle, minus the 5-degree angle below the incline. Calculate the length of the rope BC. Well, now, if we were going all the way down to the horizontal, maybe we'd then have a right triangle, but because this is only an 85-degree angle, we don't have any evidence that triangle ABC is a right angle, so we cannot use Pythagoras, nor can we use SOHCAHTOA. We could use the sine rule if we have an opposite pair. So let's examine. I've got 8 meters, but I don't have its opposite angle. I've got 6 meters, but I don't have its opposite angle. I've got 85 degrees, but I don't have its opposite side. So I cannot use the sine law because I do not have an opposite pair. Instead, let's use the cosine law. Now, you've got 2 different cosine laws in the formula booklet. We're going to use the first one, okay? When we're looking for a length, use the first one in the formula booklet that says that a squared is equal to b squared plus c squared minus 2bc cosine of a. If we had been looking for an angle, then you would use the second version of the cosine law, which begins with cosine a equals blah blah blah. Alright, here we're looking for a length, so let's use this one. Let's substitute. So the angle, the side that we're trying to find is going to become the square root of all of this stuff. So let's substitute. B is the side opposite angle B, that's 6 meters, so 6 squared plus 8 squared. So I'm starting by adding the other 2 sides squared, and then I subtract 2 of those sides times the cosine of angle A, which I figured out was 85 degrees. And then I'll take the square root of all of that. So here we go, the square root, the square root of 6 squared plus 8 squared minus 2 times 6 times 8 times cosine of 85. So what we get? 9.57 is the length of the rope. Okay, so BC is 9.57 meters. And lastly, part C, calculate the angle CBA that the rope makes with the sloping ground. So we're looking for this angle right here. Well, now that we know what the length of the rope is, we now do have an opposite pair with the 85 degrees. So let's set up the sine law then. So the sine of 85 degrees over its opposite partner, which we've just figured out is 9.57, is equal to the sine of the angle I'm trying to find, let's call it angle B, divided by its opposite side. So let's cross multiply then. 6 times the sine of 85 degrees, and then we'll divide both sides by 9.57 in order to isolate sine of B. To get B alone then, we've got to bring the sine across to the other side, and it will become a sine inverse of everything that I had just written. The sine inverse of 6 sine 85 over 9.57. Alright, let's see what angle B is equal to then. So we'll do the sine inverse of 6 sine of 85. Let's close the brackets to show that our angle is over, and then we're taking that product of 6 times the sine of 85 degrees, and we're dividing that product by 9.57. Now again, you know how I like to be accurate, so instead of writing 9.57, I'm actually going to call up my previous answer, second negative. And now I'm going to close off the entire sine inverse expression. This is my last bracket after I've completed my fraction. and I've got a B value of 38.6 degrees. Let's move on to number 7. The triangular faces are all inclined at 70 degrees to the base. Now, I want you to imagine that we are looking at this pyramid right here. Imagine yourself moving a little bit over to the left with a pyramid, so we're kind of rotating around the pyramid to gain a slightly different perspective, and then let's rotate kind of downwards until our eyes are at the level of the square base. So we should end up seeing something kind of looking like this. Our square base is sort of disappearing into the distance a little bit because it's obviously kind of a little bit, and looks something like this. We're trying to find out what is the angle between these sloping faces and the flat square base on the bottom. So in order to do this, it's critical to understand that you must construct the slant height. We have to use the slant height in order to figure out the angle, and then you'll use its shadow line, its projection. So when you're looking for the angle between a face and another face, use the slant height of the triangular one and then use its shadow line, and that will be, in this case, what it's been given, a 70-degree angle. Now the edges of the base are all 10 centimeters, so that must mean that this little thing right here is 5 centimeters. And also this thing right here is 5 centimeters, and that's 5 centimeters, so these might all be useful amounts. So using the letters on the diagram, draw a triangle showing the position of a 70-degree angle. So they want a triangle. Let me just complete the triangle by creating the height. That's always a nice one to do because the height is perpendicular to any line running along the flat base. Now show that the height of the pyramid is 13.7 centimeters to 3 significant figures. Well, I've got the 5 centimeter measure, and I've got a 70-degree measure, and I'm inside a right triangle. Because it's a right triangle, I can use either Pythagoras or SOHCAHTOA. In this case, I'm going to use SOHCAHTOA because I've been given an angle. So let's set up some kind of ratio, and let's call this x, the height. Remember, I'm not allowed to write down 13.7 anywhere until the final answer, because it is a show that question. So ignore for a moment that you know what the answer is, and cross it out. Let's show that the height, let's find the height. So we've got x squared plus, I can't use Pythagoras, can I? Because I don't know the third side. I said I would use SOHCAHTOA. So looking at the 70-degree angle, I'm trying to find x, which is the opposite leg. It's not the hypotenuse, this one's the hypotenuse. So it's the opposite leg over the adjacent leg. So the tangent of 70 degrees, it's the tangent ratio because we're relating the opposite to the adjacent. So SOHCAHTOA, T is O over A, opposite over adjacent. And so let's multiply now both sides by 5 in order to get the x alone. 5 times the tangent of 70 degrees, tangent of 70 degrees is 13.74 approximately. I'll round it to 3 significant figures, and I'm dealing with the unit of centimeters. So there is my height, and that's exactly what I was supposed to get, isn't it? It's often a good idea in show that questions to write down the rounded amount first, and so I probably shouldn't have done that. I probably first should have written 13.73738, etc., etc., etc. Just a few extra digits, and then that rounds to 13.7 as required. Okay, we needed the 13.7, and we got that matching result. Don't forget units, centimeters. Part C, calculate the length of EG. Well, that's just the hypotenuse in the triangle that we've already been working with, so we should just be able to use another SOHCAHTOA ratio. So this time, if we're calling this one let's call it L for the slant height. We often use L for slant height. Oh, I could also use Pythagoras here, couldn't I? Because now I know what x is. I could use Pythagoras. The problem with Pythagoras is that I would be possibly using an inaccurate amount, and I could lose accuracy unless I used the full decimal amount. So why don't we use a more accurate method that doesn't involve using any rounded values, and I'll look at the cosine ratio of 70 is adjacent. So let me write this down. The cosine of 70 degrees is adjacent 5 over hypotenuse, the slant height, the length EG that we are trying to find. And so the slant height L will move up to this side of the equation, multiplying cosine 70. So let's divide by cosine of 70. We rearrange this equation and we'll find that L is equal to 5 divided by the cosine of 70 degrees. So 5 divided by the cosine of 70 gives us an answer of 14.6 if I round to 3 significant figures. So 14.6 centimeters. Part double I, the size of angle DEC. Ooh, DEC. All right, let me get some of this other stuff out of the way so I can think about this fresh. So these were 5 centimeters each. Okay, DEC. Have I been given any information about the lengths? Oh, look at that. No, it's the same. Oh, I know what I should have done. Why don't I find this angle and then I'll simply double it? Because this is the midpoint, and so it's created 2 congruent triangles on each side. And these happen to be right triangles as they turn out. I've just figured out what the length of EG was. And so in order to get this angle, I should be able to use some kind of tangent ratio. This amount right here I just worked out was, what did I get for EG? 14.6 centimeters. So relative to this angle that I'm trying to find, before I double it to get the entire angle I'm being asked for, relative to this, I've got the opposite side is 5, over the adjacent side is 14.6. That's a tangent ratio again. So the tangent of angle that I'm trying to find, I'll call it theta, is equal to opposite over this 14.6 value. And so that must mean that the angle I'm trying to find, if I bring the tangent across to the other side, the theta is going to equal the tangent inverse of 5 over 14.6. Okay, the inverse of the tangent operation. And so we'll do second of tangent of 5 over, and let's take the exact value, shall we? It's more accurate. Second answer to get the 14.6 with all of the decimal places in the previous step. And now we'll get our angle is 18.88 degrees. And then of course we need to double it, don't we, in order to find the entire angle DEC. And so our angle times 2, and at this point, because it's a final answer to a question, I'll round to 3 significant figures, and we get 37.8 degrees. Alright, let's move on then to, there's a part D, the total surface area of the pyramid. So we've got a square base on the bottom. So the square base is going to have an area of 10 times 10. And then we've got 4 different triangles. So let's add these 4 triangles. Each of these triangles is 1/2 times base times the height. And if we look at this triangle carefully, I hope you can see that this 14.6 centimeter measure is the height of the triangle. We're not talking about the height of the pyramid. That's only useful when we're looking for volume. When we're talking about surface area, you have to imagine that we are taking our pyramid and we are unfolding it into all of its flat pieces. And if you look at one of these triangles, the height of the triangle is going to be this piece right here, which when you fold it back up again is what we call the slant height. Okay, so that's the slant height that we need to use, and we found that already was 14.6 centimeters. Alright, here we go then. So we've got 10 times 10 plus 4 of the triangles, which are each 0.5 times 10 times, and I'm a stickler for having exact values, so I can still see 14.619. Let's just add on a couple of extra decimal places, 619022, and I've got a total surface area then of 392.4. That rounds to 392. So 392, and the units will be centimeters squared, because of course it is a surface area. And lastly, the volume. Volume of the pyramid is always found by doing, where am I going to write this? Gosh. Volume is equal to 1/3 times the area of the base. I can't remember if they call it a capital A or a capital B, but it's the area of the base. In this case, it's a square base, times the height. And now we're talking about the true height of the pyramid. This dotted figure that we worked out earlier on was 13.7. So it's the area of the base, 10 by 10, 100. So we've got 1/3 times 100, with the area of the square base, times the height, which was 13.7 or so. I don't know if I'm going to be able to remember what the exact amount was. So I guess I'll just use the rounded value for now. Actually, let's just go 1 divided by 3. That counts as 1/3, doesn't it? 1/3 times 100 times 13.7. And we get 456.7, which rounds to 457 centimeters cubed, because it's a volume, centimeters cubed. 458 centimeters cubed, I think, would have also been accepted if you had just used a slightly different rounded answer in that volume formula. Okay, number 8. We've got a child's toy with this circle on the bottom with a radius of 7 that's being shown. The hoop is suspended by 3 equal strings, so this hoop is hanging from, I guess, some kind of suspension point X. Each string is of length 25, so we've got that. Each of them is the same, they're all 25. And the points A, B, and C are equally spaced around the circumference of the hoop. So if you imagine drawing these lines, and knowing that these are equally spaced, that must mean that these angles are all the same. So we're taking our 360-degree angle, and we're splitting it into 3 equal pieces that are each 120 degrees, aren't we? And X is hanging vertically above our point O. Right there. Okay. First, calculate the length of XO. Well, we've got a right triangle here, don't we, where this length is also 25 centimeters, and this bottom length is 7 centimeters. So let's use the Pythagorean theorem carefully here, because the 25 is the hypotenuse. And so we've got 7 squared plus h squared equals 25 squared. Really common for students to make mistakes and get the substitution backwards, so please be careful. H squared then will equal 25 squared minus 7 squared, and that gives you 576, and so h will equal the square root of 576, and the square root of 576 is 24. And so our height then is 24, and our units centimeters. So we found our height, XO, the length of XO, 24 centimeters. Find the angle in degrees between any string and the horizontal plane. Okay, so really they're looking for that angle between any string, let's choose that one, and the horizontal plane. Well, this is going to be easy to find now. Well, I guess it would have been easy to find before as well, because it was a right triangle. So relative to the angle we are trying to find, this 7, that is a known side, is the adjacent side. And the 25 is the hypotenuse, and that is the cosine ratio. So the cosine of the angle that we're trying to find is equal to adjacent over hypotenuse. And then that means that the angle that we want then will be the cosine inverse of this ratio. So we can use SOHCAHTOA whenever we can see definitively that we have a right triangle. The cosine inverse of 7 over 25 is 73.7 degrees. Alright then, part C, write down the size of angle AOB. Oh, I've already done that. It's 120 degrees. Fine. Now calculate the length of AB. This length right here. I'm going to draw this triangle a little bit bigger. Okay, so right now I've got A, this is O to A, O to B, and that's a 120 degree angle, and we know that the radius is 7, so we got 7 and 7, and we need to find now the length of AB. Let's call it X. Now that is not a 90 degree angle, 90 degree triangle, so I no longer can use SOHCAHTOA or Pythagoras. Can I use the sine law? Well, if I have an opposite pair, I can. So let's look to see if I have an opposite pair. I've got the 120 degree measure, but I don't know its opposite member. I've got the side length of 7, but I don't know its opposite angle measure. And the same thing, I've got a side length of 7, but I don't know its opposite angle measure. I don't have any opposite pair. As a result, I must use the cosine law. I remember I've got a choice of two different cosine laws. The first one is when we're looking for length. And that's what we're doing here. We are looking for a length. So let's use the first formula. And so that's going to be then that x squared will equal the other two sides squared minus 2 times 7 times 7 times the cosine of the angle in between. And then I'm going to have to take the square root of all of that stuff. Let's see what that stuff equals. So I've got 7 squared plus 7 squared minus 2 times 7 times 7 times the cosine of 120 degrees. Okay, so all that stuff gives me, amazingly, a pretty nice round number of 147. And so I just need to take the square root of 147, square root of 147, and that gives me a final answer of 12.1 centimeters. And lastly, we need to find the angle between strings XA and XB. Let me just clear up my diagram a bit. Okay, so we're looking for this angle right here. Well, we know that this is a 25 measure, and we just figured out what AB was. We figured out that that length is approximately 12.1. And so we've got then, in this triangle, we've got all three sides. I guess that means that we don't have any of the angles, right? So I obviously don't have an opposite pair. I don't have any evidence it's a right triangle, so I have to use the cosine law. But this time I'm using the cosine law to find an angle. So let's use the other version of the cosine law. And that one says that the cosine of the angle I'm trying to find is equal to the two sides that are on either side of the angle I'm trying to find. We always start with those two sides, and then we subtract the square of the opposite side. So make sure that you substitute them in the right order. And this is over 2 of the sides that are on each side. And then I'm going to have to take the cosine inverse of all of this stuff. And so what is the cosine inverse of... Alright, let's first create the numerator. Okay, this is a very difficult expression to type in, so I'm glad we're doing this problem. We've got 25 squared plus 25 squared minus 12.1 squared. And you'll notice that at the beginning I opened up an extra set of parentheses. I'm now going to close that set of parentheses. I've now completed my numerator. I'm now going to divide by my denominator. Let's open up a new set of brackets so that my denominator is treated as one entire term of 2 times 25 times 25. And now I'll close my denominator, and lastly, I will close my parentheses, which is the end of my cosine inverse. Okay, so let me write that out for you so you can kind of see it. As I move my cosine inverse across, I open up a set of brackets, and then in my fraction, I'm just going to, in my calculator, think of adding an extra set of brackets around my numerator in order for it all to be treated as a single value before getting divided by this single term of a denominator, which I'll also put in a set of brackets. So there you go. That's why I've got the extra set of parentheses, and my answer then is exactly almost 28 degrees. And so we get 28. If I round to 3 significant figures, it would be 28.0 degrees. Alright, number 9. We've got a circle. We know something about a circle is that the radius is constant everywhere, and so that's going to give us an isosceles triangle, isn't it? If we've got 110 degrees already and we've got an isosceles triangle, that must mean that these two angles are the same. Now 180 in the entire triangle minus the 110 degree angle that's already given leaves us 70 degrees to split equally between these two angles. 70 degrees divided by 2 is equal to 35, so these must each be 35 degree angles. Anyway, I don't know whether that's going to be important, but every time I look at a triangle, I immediately start trying to fill in any angles that are missing. Okay, part A. Given that the area of the circle is 36 pi centimeters squared, calculate the length of the radius. Well, now I know that the area of a circle is pi r squared. Let's substitute what we know. We know our area is 36 pi, and I know that r is the capital R in my diagram. So I'm trying to solve for that capital R. Let's divide both sides by pi, and they will thankfully cancel. This means that r squared is equal to 36, and so r is equal to 6. And so let's just put it into centimeters. Because our area was centimeters squared, the length of the radius r must be 6 centimeters because it's a length. Alright, let's calculate the length AB. So I'm going to call it x. Now this forms the third side in a triangle, which is not a right triangle. So perhaps I should be using the law of cosines or the law of sines. Do I have an opposite pair? Well, I do now, yes, because I know that r is equal to 6. So there's an opposite pair. So perhaps I should use the law of sines. And so I'll set up then the sine of 35 degrees over its opposite known partner of 6 is going to equal the sine of 110 degrees over its opposite side, which is the x that we're trying to find. Let's cross multiply. And then we'll divide both sides by the sine of 35 degrees. These will cancel, and I'll have x alone, and it will be approximately, let's see, 6 times the sine of 110 divided by the sine of 35. And we get a length of 9.83 when we round to 3 significant figures. Don't forget your units of centimeters. Lastly, part C, write down the side length L of a square which has the same area as the given circle. Alright, well I guess we know that the area of the circle is 36 pi, and we know that a square's area is its side length times itself. So then we simply should have to take the square root of 36 pi in order to find the length of the side. So the square root of 36 pi. Oops, didn't need that bracket. Let's delete it, and we're done. And we get a length of 10.6 if we round to 3 significant figures. So that's 10.6, and of course centimeters because it is a side length. Alright, and we will do the remaining 5 problems on the last part of this video.